is a collection of numbers that are arranged in rows and columns to form a rectangular array. Matrix algebra is of particular interest to us because it can be used to solve system of linear equation. Order of a matrix. The order, as known as size of matrix, is number of rows and columns. As shown in the figure, that is an example of a matrix. The order of matrix is 4 by 5, as it have 4 rows and 5 columns. Entries within matrix. The places in the matrix where the number are called entries. The entry of matrix A that lies in the row number I and column number J is called Ij entry of A. This is written as A, Ij or A, Ij. Matrices are distinguished by their order, elements, and certain other characteristics. There are various types of matrices, but the most common ones are covered below. Let us investigate the various types of matrices in the field of mathematics. Square matrix. A matrix is called a square matrix if it has the same number of rows and columns. Column and row matrix. Column matrix, a matrix that has only one column. Row matrix, a matrix that has only one row. Zero matrix. A zero matrix is a matrix where all the elements are zeros. Identity matrix. The identity matrix is a matrix that has ones on the diagonal and zero everywhere else. The identity matrix is usually written as I. Diagonal of a matrix. The diagonal of a matrix are the elements that have identical row and column numbers. Transpose of a matrix. The transpose of a matrix is obtained by interchanging the rows and columns of a matrix. Orthogonal matrix. If a matrix M has the property that MTM equal I, then the matrix is called an orthogonal matrix. Symmetric matrix. A symmetric matrix is a square matrix equal to its transpose. It is written as A equal to A transpose. Block diagonal matrix. A block diagonal matrix is like a diagonal matrix, except that the element exists in the positions arranged as blocks. In the diagram, where stars mean a non-zero element. Band matrix. A band matrix has numbers near the diagonal of matrix and nowhere else. The width of the band is called the bandwidth of the matrix. The basic operation on matrix are addition, subtraction, and multiplication. When adding or subtracting matrix, they must be in the same order. And when multiplying, the numbers of columns in the first matrix must equal to the number of rows in the second matrix. Addition of matrix. Addition is defined only for two matrices of the same order. Complete the gaps between corresponding elements. Matrix addition is a matrix multiplication operation. Subtraction of matrix. Subtraction is simply addition with the second matrix inverted union. Subtraction is not cumulative. The order is important. They must be in the same order and size. Multiplication of matrix. Matrix multiplication is only defined when second matrix has the same number of rows as the first matrix has columns. The resulting matrix has the same number of rows as the first matrix and the same number of columns as the second matrix. Determinant of a matrix is the scalar value computed for a given square matrix.
linear algebra deals with the determinant. It's computed using the elements of a square matrix. It can be considered as the scaling factor for the transformation of a matrix, useful in solving a system of linear equations, calculating the inverse of a matrix, and calculus operations. The determinant of 2 by 2. If A equal A, B, C, and D, which is first row and first column is A, first row second column is B, second row first column is C, and second row second column is D. Then let A equal AD minus BC. Let's see the example below. First question, date 2, 5, 3, 4 equal AD minus BC. It is 2 times 4 minus 5 times 3 equal 8 minus 15. The answer is negative 7. The question 2, that 3, negative 3, 2, 1 equal AD minus BC. And it is 3 times 1 minus negative 3 times 2 equal 3 plus 6. The answer is 9. For determinant of 3 by 3, we copy the first and second columns of matrix to form fourth and fifth columns. In non-singular matrix, a matrix with those determinant has value 0 is called a singular matrix. If the determinant is not 0, the matrix is a non-singular matrix.
Now, we will be looking into inverse matrix. So what is inverse matrix? Let's say A is a matrix and the reciprocal of A is 1 over A, but we write it as A minus 1. And we can multiply A with the inverse matrix of A to get I, which is the identity matrix. Let's look at the example. When 1 times with 1 over 8, we will get the answer 1. And when the matrix A times with the inverse matrix of A, we will get the identity matrix. The definition of inverse matrix is when the inverse of A is A minus 1 only when A times with the inverse matrix of A is equal to the identity matrix. The matrix A is non-singular matrix when it has an inverse matrix, meaning that the determinant of matrix is not equal to 0. So we're going to 2 times 2 inverse matrix. We have 2 steps to find the inverse matrix. Firstly, we have to find the determinant, and secondly, apply the formula shown. So let's say when we are doing the matrix A by 4, 7, 2, 6. Firstly, we have to find the determinant. Determinant is calculated by 4 times 6 minus 2 times 7, so we will get the determinant as 10. Then we just apply the formula where the determinant is 1 over 10, and then 6 and 4 we exchange their position, but for 2 and 7 we just add a minus into it, and we just apply the multiplication, so we will get the inverse matrix. Check our answer based on the definition of inverse matrix. We can times the matrix A with the inverse matrix of A to see if we get the answer. So we can see the answer is identity matrix. We will prove that the answer we get from the formula is the inverse matrix of A.
As you can see, here is the 3 by 3 matrix. There are a few steps to find the A inverse, which is find the determinant of 3 by 3. The second step is find the minor. The third step is find the cofactor. The next step is find the adjoint. And the last step is replace result in the formula. Okay, let's look for one example. Here we have a 3 by 3 matrix. The first step we are going to do is find the determinant of this matrix A. In the way I want to find the determinant, I just copy the first 2 columns and place them on the right side of the matrix. The number in column 1, which is 1, negative 1, and 0, copy and paste them to the right side, and now copy column 2, which is 2, 3, and negative 2 to the right side. Now, I'm about to create 3 arrows downwards, which is blue color. The first arrow, 1 times 3 times 1 equal to 3. The second arrow, 2 times 0 equal to 0. The third arrow, negative 2 times negative 1 times negative 2 equals to negative 4. Now, look at the green arrow. The first arrow, 0 times 3 times negative 2 equal to 0. The second arrow, negative 2 times 0 times 1 equal to 0. The third arrow, 1 times negative 1 times 2 equal to negative 2. Okay, now add the blue arrow and minus the green arrow. 3 plus 0 plus negative 4 minus 0 minus 0 minus negative 2. The determinant of matrix A is 1. The second step is find the minor. Let's take a look at the A minor. The A minor is top left position, which is number 1. So, we cross out the row and column of number 1. Now, we left a 2 by 2 matrix, which is 3, 0, negative 2, and 1. So, we cross multiply and subtract it. 3 times 1 subtract 0 times negative 2 equal to 3. We need to do the same thing for the every number until all the A minor to I minor is found. Here is our minor that found. The first row is 3, negative 1, and 2. The second row is negative 2, 1, and negative 2. The third row is 6, negative 2, and 5. The next step is find the cofactor. We need to alternate negative sign on B minor, D minor, F minor, and H minor. The matrix A becomes 3, 1, 2 for the first row. The second row is 2, 1, and 2. The third row is 6, 2, and 5. The following step is adjoint. Adjoint is interchanging of the row and column. The first row, 3, 1, 2 become the first column. The second row, 2, 1, 2 become the second column. The third row, 6, 2, 5 become the third column. The last step is to replace result in the formula. Replace the determinant that found, which is 1, and put the matrix that found in the adjoint, and our matrix A is shown. Last, 1 over 1 is a scalar and we need to multiply by the matrix A. And the final answer for inverse matrix 3 by 3